Welcome to section 11.3, which is a continuation of Fourier series. Today we're going to look specifically at Fourier cosine and sine series. So this will build on the last video from 11.2 when we just looked at Fourier series in general. Before we take a look at cosine and sine series, we're going to have to do a little bit of review. So the first bit of review is the difference between even and odd functions. Even functions, f of negative x will just give us f of x. Odd functions, on the other hand, f of negative x, will give us negative f of x. So that is algebraically. Now, what does that look like geometrically? Well, in terms of an even functions are symmetric about the y-axis. Odd functions, on the other hand, are symmetric about the origin. And then reviewing some properties of even and odd functions. First, the product of two even functions is even, and that should intuitively make sense. The product of two odd functions is also even, right? Okay, the product of an even and an odd function is odd. The sum or difference of two even functions is even. The sum or difference of two odd functions is odd. I think a lot of these should be fairly intuitive. And then the last two, if f is even, if we are taking the integral of f from negative a to a, what we can do instead is we can take the integral of f from 0 to a and then double that result. That's if the function is even. If the function is odd, though, and we're looking at the same integral, integrating f of x from negative a to a, because the function is odd, we're going to end up with 0. So all of these together, these ideas of even and odd functions, are going to lead us today to what's new, and that's cosine and sine series. So if we have some function f that's even, this is what we already found earlier from the last video of the value of a naught, or of a of 0. If f is even, though, using those properties written above, we can rewrite this. This is the same as 2 over p, the integral from 0 to p, of f of x dx. And that is hopefully going to be easier to calculate for us. Then if we look at a of n and b of n, again, these are just the general formulas that we found earlier. Well, f of x we know is even. Cosine is also even. So this then is a product of even functions, which means this entire expression is also going to be even. So then again, we can rewrite this. This becomes 2 over p, the integral from 0 to p, of f of x, cosine of n pi over p x dx. Okay, and then lastly for b of n, again, f of x is even. Sine is odd. So then we know from those properties above that this entire expression is going to be odd because the product of an even and an odd function is odd. So if we are integrating from negative p to p of something that's odd, we get 0. So that's super nice. If f is even, we know b of n is going to end up being 0. So really all we have to do is calculate a naught and a n. And it's a similar idea when f is odd instead of even. So that leads us to these definitions that you see below, the definition of a cosine and a sine series. So on the left side, if f is an even function, so if f is an even function on negative p to p, then we define the cosine series as what we have below. And that's what we did above. What we noticed above is that we still have that a of n that has a cosine in it, but then the b of n that ends up being 0, we just don't have. On the other hand, if we have an odd function from negative p to p, then we end up with a sine series. In the case of an odd function, all we have is b of n. Our a naught and our a n end up being 0. And a quick note in that case of a sine series, at x is equal to negative p, 0, or p, the value of sine is 0. So the sine series will converge to 0 at these points. So let's take a look at how this will actually play out in the first example. We are going to expand f of x below into a Fourier series. So if we had done this example earlier, like in 11.2, we would have started out by finding a sub 0, a sub n, and b sub n. What we're asking ourselves now is this function maybe even or odd? Because if so, I can just use a sine or a cosine series instead. So if we graph it, we have pi, negative pi, so we end up with something like this, which tells us that our function is odd. It's symmetric about the origin. Because our function is odd then, we can use a sine series. So from the previous page, that definition, we know for a sine series, all we have to do is find b of n. A sub 0 and a sub n are going to end up being 0. So our b sub n then, if we notice in this case that p is equal to pi, so we're going to get 2 over pi, the integral from 0 to pi. F of x is 1, looking from here. So we get 1 multiplied by sine of n pi over px dx. So simplifying this, we get 2 over pi, the integral from 0 to pi, of sine of nx dx. So integrating that then, integrating that sine of nx, we get negative 1 over n cosine of nx, being evaluated from 0 to pi. So that gives us negative 2 over n pi, and we get cosine of n pi, subtract cosine of 0. So this is the same as 2 over n pi, 1 subtract cosine of n pi. And then we've seen this before. What is cosine of n pi actually equal to? Well, all of this that I just underlined, if n is even, okay, so let's plug in a value of n that's even. If we plug in 2, we get cosine at 2 pi, which is just 1. So anytime n is even, that entire underlined portion will be 0. If n is odd, like we plug in n equals 1, we get 1 subtract negative 1, so we would end up with 2. So ultimately, what our function is going to look like then is we get f of x is equal to 2 over pi, so I'm going to have to use this and this, 2 over pi, the sum from n equals 0 to infinity of 1 subtract negative 1 to the n over n times sine of nx. Now, let's talk about how I got there from where we left off. This is the same as 1 minus cosine of n pi. And if you test it out, let's see. If we substitute n as an even value, like n is 2, we're going to get 0, like we said we should. If n is odd, like 1, we're going to end up with 2, like we said we should. We still have that 2 over n pi, so here's the 2 over pi and the n, and then this is the part of the sine series. So we'll notice we used a Fourier series, but it was significantly more efficient than what we did in 11.2. Okay, so now that we know how to handle sine and cosine series, let's move on to what we call half-range expansions. So up until this point, we have looked at f that's defined on some interval negative p to p, so some symmetric interval. What happens though if f is defined on a different interval, like 0 to L? What do? Well, in order to do a Fourier series, we're going to need a symmetric interval. So what we're going to have to do instead is we're going to need some arbitrary definition on the interval negative L to 0, so that when we put these two together, we end up with a symmetric interval. So there's a few things that we can do, 3 different cases about how we can handle the expansion. We can make f even on the interval negative L to L, or we can make f odd on the interval negative L to L, or lastly, we can define f on negative L to 0 by allowing y to be f of x add L. So let's take an example of, let's look at geometrically what all of these mean. So I'm going to sketch out what case 1 would look like, what case 2 would look like, and what case 3 would look like. So let's say we have some function, like we said, defined on 0 to L, and it looks like this. For all three cases, we're going to consider the same function that is defined on 0 to L. And so we said we need it to be defined on negative L to L, on a symmetric interval. Okay, so in case 1, where we make f even, we need it to be symmetric about the y-axis. So that means between negative L and 0, we would end up with something like this. On the other hand, in case 2, if we make f odd, then we need this function to be symmetric about the origin. So it would end up being something like this. And then in case 3, where we're just kind of shifting that function back, we end up with the same little function from negative L to 0. So looking at these different cases, in case 1, our p would end up being L. In case 2, our p would also end up being L. But then in case 3, our p would end up being L over 2. So these cases 1 and 2, these will yield cosine and sine series. And these are known as half-range expansions. So in the next example, we are going to take a look at doing all three of these cases. So here we go. We are expanding f of x, which is equal to x squared, in a cosine series, a sine series, and a Fourier series. And so what I need us to notice here is that f of x is defined on 0 to L. So it's not defined on our negative to L like normal. So this is where we're going to need to use those half-range expansions. So I'm going to start with a cosine series. So if it's a cosine series, our p is going to be equal to L. So if I go to find a naught, that's going to be 2 over L, the integral from 0 to L of x squared dx. So that gives me 2 over L, and when I integrate, I get 1/3 x to the third from 0 to L. So that a naught then ends up being 2/3 L squared. Then if I go to find my a of n, I get 2 over L, the integral from 0 to L of x squared cosine of n pi over L x dx. Okay, so we've seen this a little bit earlier, needing to integrate this product. We can do integration by parts, or we can do tabular. So if I start with the x squared, I can differentiate that down to 0. And then if I look at that cosine of n pi over Lx, that's the one that I'm going to have to integrate. So I get L over n pi sine of n pi over Lx. Then I get negative L over n pi squared cosine of n pi over Lx. And then I get negative L over n pi cubed sine of n pi over Lx. So then if you remember the deal with tabular, we're going to go along our diagonal. We're going to keep the sign, flip the sign, keep the sign. So where that gets us to then, this is going to be a pretty long expression, so I didn't give myself a ton of room. But what we're going to end up with, we'll end up with x squared L over n pi sine of n pi over Lx, add 2x times L over n pi squared cosine of n pi over Lx. And then we are subtracting 2 multiplied by L over n pi quantity cubed sine of n pi over Lx. And all of that has to be evaluated from 0 to L. Okay, so let's keep going. I'm going to continue that here. And let's see what we get. When I substitute in L, I'm going to end up with L cubed over n pi sine of n pi. Add 2L cubed over n squared pi squared cosine of n pi. Subtract 2L cubed over n cubed pi cubed sine of n pi. And then when I substitute in that 0, I'm going to get 0 here because of the x. I'm going to get 0 here because of the x. And then sine of 0 is just going to be 0. So thankfully, I don't need to do anything with that 0. Okay, so one thing that we notice is that sine of n pi, sine of any multiple of pi is going to be 0. So that's just 0, and that's just 0. Okay, so we're almost done with this first part A. So what that gives us then is 4L squared over n squared pi squared cosine of n pi. Okay, so then if we look at that cosine of n pi, that is 1 if n is even, and it is -1 if n is odd. So as you've already seen, how that can be written is -1 to the n. So then where that leads us is that our a of n is 4L squared times -1 to the n over n squared pi squared. So finally, we've gotten to the point where we can actually write this as a cosine series rather. So we get f of x is equal to L squared over 3 add 4L squared over pi squared, the sum from n equals 0 to infinity of -1 to the n over n squared cosine of n pi over Lx. So that is our cosine series. That is a half-range expansion using cosine. Okay, so now what we're going to do in part B is we are going to approach the same function, but this time using a sine series. So again, in this case, our P is equal to L. So if we start with B of n, well, not start with, really, that's the only one we need to calculate, we get 2 over L, the integral from 0 to L of x squared, sine of n pi over Lx dx. And like we saw before, of course, we're going to need to use tabular in this case to integrate this product. So I'm going to do that all the way off to the right. I have my x squared that I'm going to differentiate, and then I have my sine of n pi over Lx that I'm going to integrate. So I get -L over n pi cosine of n pi over Lx. And then I get negative quantity L over n pi, all of that squared, sine of n pi over Lx. And finally, L over n pi, that quantity cubed, cosine of n pi over Lx. And then we do our diagonals, keep, flip, keep. Okay, so where that leads us to then is we have 2 over L, and we have negative x squared L over n pi, cosine of n pi over Lx, add 2x, L over n pi, quantity squared, sine of n pi over Lx, and then add 2 over L over n pi, that quantity cubed, cosine of n pi over Lx. And all of that is being evaluated from 0 to L. Okay, so now let's start plugging in that 0 to L. And so we have our 2 over L, and then we end up with negative L cubed over n pi, cosine of n pi, plus 2L cubed over n squared pi squared, sine of n pi. Then we have 2L cubed over n cubed pi cubed, cosine of n pi. And then finally, when we go to plug in this 0, plugging in the 0, because of this x, we're going to get a 0. Because of this x, we're going to get a 0. When we plug in 0 here, cosine of 0 is just 1. So we end up with a negative 2L cubed over n cubed pi cubed. Okay, so looking to do a little bit of simplifying here. Sine of n pi is just 0, so that's going to go away. And then we also have this cosine of n pi and cosine of n pi, so we're going to want to bring those together. So doing a little simplifying, we're going to get negative 2L squared over n pi. Add 4L squared over n cubed pi cubed, and those are both the terms multiplied by cosine of n pi. And then we have a negative 4L squared over n cubed pi cubed. Okay, we're going to do a little bit of nice simplifying here, so let's see how it ends up going for us. One thing that I notice is I have this 4L squared over n cubed pi cubed and also this one. So if I could get those two terms together, that would be convenient to me. So what this is going to end up giving is negative 2L squared over n pi cosine of n pi. And then I have that 4L squared over n cubed pi cubed, and I have a cosine of n pi subtract 1. Okay, so we've already looked at this cosine of n pi. We've seen that it equals negative 1 when n is odd, and we've seen it equals positive 1 when n is even. So again, the way that we can rewrite that is negative 1 to the n power. Okay, so we're almost there. So what that gets us then, if I take into account this negative, I can write that first term as 2L squared over n pi times negative 1 to the n plus 1. And then I have 4L squared over n cubed pi cubed multiplied by negative 1 to the n subtract 1. Whew. Okay, so finally, after all of that work, we are ready to write our sine series. And so this gives us 2L squared over pi, the sum from n equals 1 to infinity, of, now remember I factored out this 2L squared over pi, so I'm going to have to take that into account from both of these. So my coefficient ends up being negative 1 to the n plus 1 over n, add 2 over n cubed pi squared times negative 1 to the n subtract 1. Sine of n pi over Lx. So this is our half-range expansion in a sine series. And so finally, we will do this problem one more time, this time though as just a regular Fourier series. So in this case, we are going to have to find a0, an, and bn. And if we remember the geometric expression of this, our p is going to be L over 2. Because between negative L and L, this function will happen twice. So instead of our period being L, it's going to be L over 2. Okay, so let's jump right in. Our a of 0 is going to be 2 over L, the integral from 0 to L of x squared dx. We already did that. That is 2/3 L squared. And then for our a of n is going to give us 2 over L, the integral from 0 to L, of x squared cosine. Now remember our p is L over 2. So this gives us cosine of 2n pi over Lx dx. Okay, and so we know that we're going to have to do tabular with this. So we have x squared, 2x, 2, and 0. I have my cosine of 2n pi over Lx, which I'm going to integrate. That gives me L over 2n pi sine of 2n pi over Lx. I then have negative L over 2n pi, that quantity squared, cosine of 2n pi over Lx. And finally, integrating one last time, I get negative L over 2n pi, that quantity cubed, sine of 2n pi over Lx. So looking at our diagonals, remember keep the sign, flip the sign, keep the sign. So that gives us then 2 over L, and my coefficients are x squared L over 2n pi sine of 2n pi over Lx, add 2x times L over 2n pi, that quantity squared, cosine of 2n pi over Lx, subtract L over 2n pi, that quantity cubed, sine of 2n pi over Lx. And all of that needs to be evaluated from 0 to L. Okay, so now when we plug in that L, I'm going to end up with L cubed over 2n pi sine of 2n pi, add 2L cubed over 4n squared pi squared, cosine of 2n pi, subtract L cubed over 8n cubed pi cubed, sine of 2n pi. So all of that was when I substituted in the L. Now when I substitute in the 0, this x will give me 0, this x will give me 0, and then if I plug in 0 for x here, I get sine of 0, which is just 0. So I end up subtracting 0 and 0 and 0. Okay, so looking at doing a little simplifying, all of that is 0. Sine of 2n pi, that's 0. That's 0. If we look at cosine of 2n pi, so that'll be cosine of 2 pi, 4 pi, so on and so forth, that gives us just plain old 1. So now we can simplify all of that. We have this 2 over L, and we have this term, which will give us L squared over n squared pi squared. Okay, so now we have to find b of n. So our b of n is 2 over L, the integral from 0 to L, of x squared sine of 2n pi over L x dx. Of course, we already know we're going to have to do that tabular or integration by parts if that's what you prefer. So I have my sine of 2n pi over Lx. I'm going to integrate that so I get negative L over 2n pi cosine of 2n pi over Lx. Integrating again, I get negative L over 2n pi quantity squared sine of 2n pi over Lx. And then one more time, I get L over 2n pi cubed cosine of 2n pi over Lx. Flip the middle sign. Okay, so I want to make sure I'm careful with my work here. So now when I simplify that, I have 2 over L, and then I have negative x squared L over 2n pi cosine of 2n pi over Lx. And then I have 2x L over 2n pi, that quantity squared, sine of 2n pi over Lx. And then I have L over 2n pi, that quantity cubed, cosine of 2n pi over Lx. And that is being evaluated from 0 to L. Okay, so let's get to substituting in that L. When I do, I have negative L cubed over 2n pi cosine of 2n pi plus 2L cubed over 4n squared pi squared sine of 2n pi. And then I have L cubed over 8n cubed pi cubed cosine of 2n pi. All of that comes from plugging in the L. So now when I go to plug in 0, that will be 0, this will be 0, and cosine of 0 will just give us plain old L cubed over 8n cubed pi cubed. Whew. Okay, so let's do some simplifying. Again, that sine term is really just 0. Cosine of 2n pi is 1. Cosine of 2n pi is 1. So we see then that these two terms are going to subtract out to be 0. So having this term being multiplied by that term gives us negative L squared over n pi. And finally, we are ready to write our answer. Our f of x is L squared over 3. Add, I'm going to factor out L squared over pi, so I then have the sum from n equals 1 to infinity of 1 over n squared pi cosine of 2n pi over Lx, subtract 1 over n sine of 2n pi over Lx. And finally, that is our expansion as just a regular old Fourier series. Now, before we end our time together, I do want to talk about what these represent geometrically. So in terms of what this represents geometrically, we have x squared between 0 and L. In part A, where we treat this as a cosine series, that means that we're taking that part and we're reflecting it over the y-axis. And so we have to picture it. It's basically doing this. Then, if we take a look at what we did in part B, again, 0 to x squared, or y equals x squared, between 0 and L, what we're doing this time is we're treating it as a sine series, so we're reflecting about the origin. And so it's kind of like doing this over and over again. Right, where this would be negative L, negative 2L, so on and so forth. So in both of these cases, we have a periodic extension equal to 2L. Now, in part C, instead what we did, we still have our f of x is equal to x squared. What we did when we went to negative L, we treated it exactly the same. That wasn't very good. So every L, we're just graphing or treating it exactly the same. So in this case, our periodic extension is just equal to L. Okay, I know we didn't get through many examples in this video, but you can see that these are quite long problems, so it should have given you the basis for approaching a cosine or a sine series when defined over the interval negative p to p. And then we talked about when you're defined over the interval 0 to p or 0 to L, you're going to have an extension either as a cosine series, a sine series, or just a regular old Fourier series. So at this point, you're going to get some practice on your own, and hopefully this was enough to get you started. Thank you for sticking with me. Moving forward, this is the end of Fourier series for us. So the next thing that we're going to move into in the next few videos is what we call wave and heat, which are some specific applications. So like always, thank you for watching, and I'll see you next time.